So, a new scientific paper just dropped, and it's making some truly mind-blowing claims. We're talking about a completely new theory of gravity that, if it's right, could solve some of the biggest mysteries in the universe. And it might just mean that dark matter isn't even real. So let's get right into it.
I know, it's a wild question, right? For decades, dark matter has been the go-to explanation for why entire galaxies don't just fly apart. But this new paper says, hold on, what if we've been looking at this whole thing completely backwards? The answer isn't some invisible, mysterious stuff. It's that our understanding of gravity itself is missing a piece. Okay, so to really get why anyone would even think of something so out there, we need to look at two huge puzzles that have been driving physicists crazy. Think of these as the big cracks in our shiny model of the cosmos. All right, first up is the one you've probably heard of, the missing mass. Basically, stars way out on the edges of galaxies are moving way too fast. Based on the gravity we can see, they should be flung off into deep space. So we invented dark matter to add the extra gravitational glue to hold everything together. Now, the second one is a little more obscure, but it's super important, the forbidden twist. You know how when you stir coffee, it keeps swirling for a bit even after you take the spoon out? It has a memory of that twist? Well, it seems space-time does something kind of similar, and our current theories of gravity say that should be absolutely forbidden. So, the big question is, how on earth do you solve both of these at the same time? Well, this paper points the finger at a brand new suspect. It's a theory with a kind of dry name, but the idea behind it is an absolute game changer. It's called derivative frequency theory, or DFT for short. And this is where things get really wild. DFT says gravity isn't fundamental. It's not one of the basic building blocks of the universe. Instead, it emerges from something deeper, kind of like how the feeling of wet emerges from a bunch of H2O molecules that aren't individually wet. So, what's that deeper thing? Okay, let's break this down. The first big idea is this. Forget everything else for a second. At its very core, the universe is a giant field. A field of frequency, just vibrating everywhere, all the time. Second, when you drop something with mass or energy, like a star or you or me, into this field, it changes the vibration right around it. The classic analogy is a bowling ball on a trampoline making a dip. Here, mass makes a change in the local frequency. And here's the kicker, the final piece of the puzzle. What we feel as the force of gravity is literally just us sliding down the slope of that frequency change. Gravity is that slope, or what scientists call the gradient. A really steep change in frequency means really strong gravity. It's that simple. Okay, so that's the theory in a nutshell. It's a neat idea, but does it actually work? Can it solve those two huge puzzles? Let's start with the weirder one, that forbidden twist in spacetime. And this is a huge problem. A simple field, like the one they're proposing, shouldn't have a built-in direction. It shouldn't be able to tell left from right or clockwise from counterclockwise. Physicists call this property chirality. You know, like your hands, they're mirror images, but they're not identical. That's chirality. A basic field shouldn't be able to create a chiral effect. But this spin memory in spacetime clearly does. So how does this theory get around that? The theory pulls out this really cool tool from the geometry toolbox, one that usually gets ignored. It's called torsion. Now, if you think of Einstein's gravity as the bending of spacetime, you can think of torsion as an actual twist in spacetime. It's an extra way for spacetime to get funky. And here is the absolutely brilliant solution they came up with. The theory says that the spin of matter, its angular momentum, talks directly to this underlying frequency field, and that interaction literally twists spacetime, creating torsion. And that is what leaves behind this directional, chiral spin memory that was impossible to explain before. It's an incredibly clever way for a simple field to produce a really complex handed effect. All right, so it nails the weird, obscure puzzle. That's cool. But what about the big one, the headliner, the one that could make us throw out all the astronomy textbooks? What about dark matter? Okay, look at this. This graph is everything. That dashed line is what our standard theory of gravity predicts for how stars in our galaxies should move. See how it just drops off? Well, that's completely wrong. It doesn't match what we actually see. Now look at the solid red line. That's the prediction from this new DFT theory. It hits the observed data almost perfectly. And it does it with zero dark matter. None. So, how does it pull this off? Is it just a bunch of mathematical tricks? Nope. It all comes down to a single new fundamental number for the universe, a characteristic length scale of about 17 kiloparsecs. That's roughly 55,000 light years. This one number, which they figured out by looking at the galaxy data, basically sets the distance where this new gravity effect kicks in, making those flat rotation curves just happen, naturally.
Okay, but hold on. If gravity is different, wouldn't we have noticed it by now, here in our own solar system? And the answer is a very clever no. The way the theory is built, on smaller scales like the ones inside our solar system, its predictions are basically identical to Einstein's. It passes all of our most precise local gravity tests without breaking a sweat.
And this, for me, is the most exciting part. This isn't just some philosophy or a cool idea that lives on a blackboard. The scientists who wrote this paper proposed 3 separate real-world tests that will either prove the theory right or prove it wrong. This is real science in action. So here they are, the 3 big tests. First, the galactic decline. The theory predicts that if we look really far out in a galaxy past about 50 kiloparsecs, the rotation speeds actually will start to drop off again. Second, the suppressed memory. That weird space-time twist effect from gravitational waves should be weakened or suppressed by about 45% for anything happening inside our galaxy. And third, the lab plateau. A super clever experiment you can do on a lab bench should show this weird flat-topped plateau shape where you'd normally expect to see a sharp spike. This table basically sets up the ultimate showdown. For every single one of these predictions, the standard model we use today says, nope, shouldn't happen. And this new theory, DFT, says, yep, it absolutely will. There's no wiggle room here, nowhere to hide. The experiments are going to give us a clear winner. And the best part? We don't have to wait a century for the answers. The lab experiment could get us results in just a couple of years. We're expecting the first data on that galactic decline from new telescopes like the James Webb around 2027. In the big one, the definitive memory test, that'll come from the LISA space mission in the 2030s. We actually have a roadmap to the truth.
So, there you have it. A radical new theory that just so happens to solve 2 of our biggest cosmic headaches, gets rid of dark matter entirely, and makes a bunch of really bold, really specific predictions we can actually test. The next 10 to 15 years are going to tell us if this is the beginning of a true revolution in physics, or if it's just a beautiful, brilliant idea that didn't quite line up with reality. Either way, the experiments are coming, and they'll be the judge.